To understand calculus, we first have to solve a geometric problem, measuring the exact rate of change at a single point on a curve. If we pick 2 points, we can find an average rate of change. To find the precise rate at a single location, we bring those points together until the secant line locks into a single tangent. Walter Rudin formalizes this geometric idea in his text. Look at definition 5.1. First, he establishes the difference quotient in equation 1, representing the slope between 2 separate points. Then, in equation 2, he takes the limit of that quotient as the distance between the points approaches 0. If that limit exists, it defines the derivative at that specific point. There is a specific physical requirement for this definition to work. If a graph has a sudden break or a jump, a discontinuity, you cannot slide those 2 points together. If you try to draw a single line through a gap, the geometry fails. A derivative cannot exist where a function is broken.
Rudin proves this requirement algebraically in Theorem 5.2 by setting up the difference quotient and multiplying it by the distance between the points. The limit evaluates to the derivative multiplied by 0. The mathematical result is 0. This algebraic step guarantees that the function's value matches its limit at that location, proving that every differentiable function is continuous. Differentiability guarantees continuity. But as we step further into the analysis, we will see that this relationship is a one-way street. Handling more complex curves requires tools more precise than geometric intuition. To find the derivative of these more complex functions, we rely on established algebraic rules. For operations like the product rule, the proofs depend on a standard technique, adding and subtracting the same middle term to factor the equation, as shown at the bottom of this page. For composite functions, the chain rule demands more rigor. Introductory calculus classes often prove this rule by multiplying fractions and canceling middle terms. However, because limit definitions involve variables approaching 0, this proof collapses if the change in f equals 0 at any point. The algebra requires a division that isn't defined. Rudin sidesteps this in Theorem 5.5. Instead of fractions, he defines isolated error terms in equations 4 and 5. By rearranging these, the difference quotient transforms in equation 6. The error variables approach 0, completing the proof without division by 0. Defining specific error boundaries provides the precision required for analysis. This level of rigor allows us to evaluate the derivative even when functions behave erratically. To test the boundaries of these rules, let's examine example 5.6a. This function is defined as x times sine of 1 over x. The challenge is to evaluate the derivative at the origin, where x equals 0.
This diagram illustrates the behavior near the origin. The line is continuous, but as we evaluate the limit approaching 0, the sine term causes an infinite oscillation. Because the curve zigzags without settling on a single slope, the limit does not exist. The function fails to be differentiable at 0. Look at example 5.6b. By altering the function slightly, multiplying it by an extra factor of x, we get x squared times sine of 1 over x. When we apply the limit definition of the derivative at 0 this time, the extra x factor forces the entire expression to 0. We can see this through the squeeze theorem. By constraining the oscillation inside the bounds of x squared and negative x squared, the curves are pinching the wave flat at the origin. The oscillation is tamed, creating a valid horizontal tangent line. But calculating the derivative elsewhere yields equation 10, revealing a cosine term oscillating without bound near the origin. Therefore, the limit doesn't exist. The nearby slopes swing wildly between positive and negative 1. The derivative function itself is completely broken. The result reveals a subtle distinction in calculus. We establish that differentiability in f guarantees continuity in f. But as this case shows, a function can possess a derivative at every point, while the resulting derivative function is not guaranteed to be continuous.